So Patrick, can I tell everyone what you told me?
Sure.
Okay, so Patrick admitted that he had to program the IBM cell processor as part of his master's thesis. And it's a very nice job, except you have to program 3 different machines. The host x86, and then the little processor PowerPC on the cell, and then 8 different small processing elements which have their own codes. And then in addition, there is no automatic transfer of data, so it's DMA to move data from one processor to another, or between them, or to the PowerPC and so on. So in other words, it's a lot of work that the programmer does just in order to get to the work. Before you can start working, you have to do a lot of work. And if we can avoid it, we call it simple programming. And also, in other systems that try to do tasks, managing the test is done in software. And it takes a long time, such as I've seen examples done in the research at the Barcelona Supercomputer Center, where they do task management like this, and each task switch operation is maybe 1,000 to 2,000 cycles. So to make this overhead go away, it makes sense for the actual tasks to be 10,000 to 20,000 cycles. And that means you have to have very large tasks. So what we did in a previous slide, fine granularity, like here, very small short test is impossible or completely impractical on such machines. And the advantage of the architecture we are doing now in MacSpace is the hardware scaling. And that's the one point that makes the complete difference and enables the use of a very large number of processors. Besides, if you do very large tasks, then you cannot have too many of them. And if you cannot have too many of them, you cannot take advantage of a large number of cores. So this is obvious in this case. The other advantage, of course, that we have when we program everything all the way to maybe 1024 processors over all this, is that our code in the end is very portable. So if now we have RC64 and in a few years we'll have a version with many more processors, it's the same code. You don't have to invest in redoing the code. And typically, the fact that we spend a lot of money and time on making the chips is not important. What's important is for the user to rewrite the code. It makes some projects impossible because you just don't have the budget to rewrite the code. So the idea is, can I port this code to the next level, even if it's 10 years from now? And believe me, I've seen it too many times when 10 years have passed and suddenly they need to use the old code again, and it doesn't get used because of too much work on redoing it.
Best example are mainframes.
Fun?
Best
Yeah.
example are mainframes.
It's just like the old story of mainframes, where the user, which were extremely large companies, especially in finance, told mainframe makers, namely IBM, don't change the architecture, it doesn't matter. What matters is the cost of software. So we went over this code. No, we didn't. So here's the code. So I say the task graph is extremely simple, just like before. Regular, duplicable, regular. No picture to draw. We insert 2 header files, complex and math. Math is only to define pi, and math defines m_pi. So we call it pi again. So we just rename it. And here in this example, this is 16K FFT or DFT. Now we use float complex, complex because we inserted complex.h, float complex xn, inputs time domain. The generate input is shared by the DFT and the FFT segments of the code. So DFT, FFT generate input, and in this it's very simple. Remember, as before, this is just using a constant, but we can put random number. But random number do not generate complex. So you have to do random number for the real and random number for the imaginary. Here we have a DC input. All the inputs are 1 in the real and 0 in the imaginary. So you basically have a time domain input that's fixed at 1. Doesn't change. That's what we call DC input. Of course, you know what the Fourier transform that will be received. We will have a spike at 0 frequency, DC, and zeros everywhere else. And if it's not very accurate, so we'll have just a little bit of noise, but that's the result of the conversion. The duplicate is a strange name, but it's Twiddle calculation. Twiddle factor is the name of the exponential coefficient. So it's duplicable. The instance computes 1 transform point, so we have to generate n instances, as is shown here in the task graph. The index k is the same as ID, so we generate n instances, and each one gets its number. Floats are, there are some floats, temporary value and so on, and we start the temporary sum as 0, but we have to say 0 plus 0 times I. Capital I, just like used here, is defined in complex.h as the I number, imaginary square root of 1. So capital I is a preserved constant. And the argument is minus 2 pi times k divided by n, and we still have to multiply it by n. So it's not multiplied by n again. And for, this is the loop over n, so Rn is argument times n, and now the temporary sum includes x times the coefficient cosine plus I times sine of the argument. Argument multiplied by n. And finally, at the end of the loop, after the loop, we assign it to the output. I think what's missing here is 2 things. Can you tell me what's missing here? 2 things are missing in this code, in my mind. One, maybe maybe the compiler didn't complain, and it will do it for me. One, I saw a definition of the inputs, small x, but I don't see a definition of the output, capital X. So this seems not to be defined here. In the code that's running, I don't see this because I have all the definitions put away in the header file, so probably we did it right there. And the other thing is, I don't know, in all of this code, maybe I don't have to say, but in the previous picture here, I attached the word complex before every operator, before the multiply and before the assignment. In the code, I don't see that, so probably the compiler is willing to take it as is. Some of these problems I only see when I start talking about that. The code also contains FFT, and the question is, can you compare the executions? And I told you what I do is I run both of them in the same program, side by side, and draw the picture, and it's very obvious. Now, the other question is, the only difference between DFT and FFT is the way we compute, but it's the same coefficients and the same multiplications. Everything seems to be the same. But if I take reasonable inputs, not the imaginary input that I had here, just a DC input with 1 all over the scale. But if I take random numbers, for example, or if I take a reasonable signal, for example, the simplest signal that I can take in the input is either, some shape, or a sine, or cosine, or something like this, so I know what to expect at the output. The numerical output of DFT and FFT are different. And if I store the results and compare them, I get some differences, minor differences. Why?
Because you only computed on half the data.
So his answer is, I only computed half the data. However, I do the same half data or same computation in FFT and DFT. I do it both on FFT and DFT, the same.
So, I mean, there are two reasons. One of the reasons is you have less computation.
Where?
In FFT.
Okay.
Less computations. That means you have better precision because you have less computations. The more computations you have, the more shifts you have to apply. And shifting is not precise. If you have to shift, like the floating point unit has to apply these shifts, then it's not as precise anymore. So if you do 1 million floating point operations compared to 10,000, will make a huge difference. You can get differences like 1%.
The number of computations that each number goes through is the same. Each number is multiplied by...
If in the DFT you have a complexity, compute complexity of n squared,
so
compared to O of n log n.
So basically, I of course agree with you, but I'd like to explain it slightly different.
Okay.
In DFT, we multiply every number by one coefficient, that's it. And then we start summing up. If I have 16K, I sum up 16K results of these multiplications, these products. And then I get one answer at the output. In FFT, I do a similar thing, but instead of multiplying once, I multiplied once and I sum 2 results in a reduction. And then I multiply again and sum 2 results. And then I multiply again 16 times because, no, 16K is 14 times. The log of 16K is 14. So instead of doing a simple linear combination in DFT, in FFT I work with partial sums. So I end up multiplying by similar coefficients, but I'm multiplying different numbers along the way. Mathematically, symbolically, it's exactly equal. But practically, because of what you say, a precision of computation, I get different results because I do different numbers or different order of, I do a lot of partial results versus one final thing. It's the laws of commutation of operations and association of operations. So what do you do first? Do you do just multiplication first and all additions, or you distribute them? And whether you first do the first operation or you first do the last operation. So, and there are many different ways to organize FFT, and each one of them will generate different numbers in the very rare cases and in the end, you know, in a very small level. So relatively they are the same numbers. But if you look at 10, 20 places after the decimal point,
Not only. You will get
4 places, 5 places, yeah.
It can be even worse. It can be even worse. I mean, we have tried some experiments also with dot products and so on. There you can see it easily because in the dot product, the number of computations you crunch is equally to your to your vector length.
What about? Did you show yesterday the arrow planes for FFT?
That was between not only FFT, we did it for the SAR algorithm. And we showed the difference between double precision computations and single.
So the other thing, of course, precision issues are when you add 16,000 numbers, it's one thing, but you add and then normalize at the end. But if you in FFT you normalize in every stage, the results are different. These are the shifts that you
So since you have dynamic range and floating point computations, you have to apply shifts after a while when the mantissa gets too large, and then
of course every algorithm, every way you implement the algorithm has its own problems. But the people who developed the algorithm originally, what did they use? MATLAB. With double precision floating point, and this to them seems the golden standard. So we are not running against real numbers, we are running against MATLAB, always. So every time you implement something on a processor other than, you know, MATLAB, even if you do floating point, double precision, or whatever, part of the work is working with the people who develop the algorithm and showing them the difference like you've shown and convincing them that that's exactly what they want.
In the first place, you have to work with people who design the sensor because they know what the sensor gives you, what type of precision. So if the sensor can only deviate by 3 orders of magnitude, for example, from 1 to 1,000, doesn't make sense to convert the inputs directly to floating point in the first stage, but rather to a different format. But still, if you have a lot of computations, it's beneficial to do these computations in a better precision. Only to perform computations, not to load data.
So in other words, what we are saying is, when we do these things, we are talking today only about the programming issues of this parallel architecture. But every time we look at the results and have other people look at the results, that's the second question that we get.
But you have to prove them first.
So I'm done with the DFT and FFT. Let me go into the code. I'm done with the slides, but let me go into the codes and show what they are. You're still here?
I'm going.
You miss your flight.
It's a
okay, good.
illusion.
Yes, okay, fine. So I'm closing sample 3 and going to sample 4, DFT and FFT. Open up. Remember, the task map is simple, boring, but the code here has 2 task maps here. One is commented out, that's the FFT. So DFT was these 3 lines. Program start, they just calculated the inputs, and program end, and in the middle, to your calc. FFT, and FFT init, and another FFT series. Safe light. And then 2 duplicable, bit reversal. Bit reversal for FFT, because we implemented here the type of FFT that needs the input permuted first, according to the bit reversal of the index, and only then you do the FFT and the output comes out well organized. The other possibility is to do the inverse, the different type of FFT, where you start with the normal indexes, but then at the end you have to do the bit reversal permutation. So here it comes first, and since you just replace 2 at a time, you can do it duplicable, you can do all of them in parallel. If it's 1K, then you have 512 instances of this task. And then you do the 1 phase FFT. Duplicable here is for each phase. So there are log n phases, and each phase is done in parallel, and then you go to the next stage. You have to finish completely one stage before you go to the next stage. You finish one stage and store back all the results, because there is data dependency. The next stage wants all the data from the previous stage in memory. And so there is a while condition, a small regular task that counts log n and sends you back, and then at the end after you count. So this is FFT. I'm going to the source. The source has multiple sources. It has FFT and DFT. I marked out FFT, but let me go into it anyway. So FFT has nice code, well commented. It's not even included in the examples. It's a general thing, but David referred to it in his slides yesterday. You didn't, right? Only David did. On ESA page.
Yes.
So David described the fact that ESA in STEC was created a set of 5 benchmarks. And here we have one. And this one is a very nice exercise because it's so simple. So the ESA benchmark is posted on the web in the slide that I just, in any link that I just included here. By the way, it's not the benchmark itself that's posted, or the document. It's a nice page asking you to ask specifically for it, and only when you get permission you get to download it, but everybody gets permission. It's not restricted, but they just want to keep track of who's taking it. Well, we know these are ESTEC people, they have to report everything that they've done, so they want to be able to report a lot of things. It's designed for telecommunication, but it's a very crude kernel of what could be done in a demodulator. So the picture on the top shows the first stage. There is a demodulation. So the input data goes alternatively to the top or to the bottom, even and odd, and then multiplied by either -1 or 1, -1 to the power of the ordinal number of the sample. And then there is a little filter with, I think, 8 or 12 taps. And the two outputs go to destination where they do up sample and then filter, very wide filter, and then down sample. And quite nice. So we create a extremely simple task graph. The interesting thing about this task graph is that this, for the first time, shows how we deal with a string. So there's a loop, endless loop. The first thing we do, in parallel, we bring into storage the input from the next set of data. We decide what the size of the data is. And in parallel, we push out the previous set of data. And in parallel, we compute the present set of data by doing the two demodulators and then two decimators. And the I, these are separated to I and Q, in phase and quadrature. It's just like complex numbers. And I depends on I and Q depends on Q, so they are in two different sides. And here's the code. So, by the way, this is almost the entire code. The one thing you need to do here is to copy into some place the coefficients. And the document really specifies the coefficients. And the document also tells you how to generate the data by giving you one line of a MATLAB code and say you run this MATLAB code and you generate 10 million numbers. Very nice. So you do all this in advance, and now you have the coefficients in two arrays. One of the arrays is called demodulation coefficients, and the other is called decimation coefficients. Very simple. And the inputs are inputs, so input X or whatever, and the outputs are decimation output and so on. And at the end, they ask you run the whole thing also on MATLAB, generate the outputs and compare your results to the MATLAB outputs and tell us what the difference, and then tell us how fast it is and what kind of power you used and so on. All the interesting questions. So the map, well, it defines all the number. It shows that we arbitrarily decided that the input block is 8,000 numbers. It really does not matter. We could have selected fewer numbers in a block, but not too few, because the longest filter is, as you see here, the number 69. So the longest filter is about 70 taps long. So if you do separate blocks, you have to overlap one block with the next block by about 70 inputs, so you don't really miss the filters, because the filter looks aside 70 places. So you don't want to do blocks that are only 100 because you overlap 70 with the first one, the one before, and 70 with the one after. So 1,000 was also just too small, so we selected 8,000. We don't know why, but we selected one day 8,000. I think we started with this benchmark maybe 10 years ago, and since then the number 8,000 stuck. So this is a historical glitch. And this is half the number, and this is different numbers. And so we have a regular task for starting, and then duplicable for demodulation I, and duplicable for demodulation Q, and set of duplicable for decimation I and Q, and then the end. And then you go back and start again. What I don't show here are the tasks that handle the input and the output. It's not really interesting. Especially in an emulator, we just run it once and figure out the performance. So, the demodulator, we say when we get an ID, and multiply it, and then we run each filter here. You see, output is, here's the index, so index is computed in a certain way, but then it adds up all the filter, and the filter is 1, 2, 3, 4, 5, 6, 7, 8 tabs. So input x, x plus 2, x plus 4, x plus 6, x plus 8, 10, 12, and 14. Why do I take only the even numbers? Because the picture did show here that the even numbers go on the top and are treated completely separately from the odd numbers which go on the bottom. And then there is a plus minus modulation thing there, and the plus minus are here hardwired minus, plus, minus, plus, minus, plus, minus, plus. So he implemented the full filter and the demodulator very easily in these two statements. The other statement is for the odd numbers, and this is repeated and so on. So basically, no, that's all. Here are all x plus 2, x plus 4, and again, x plus 2, x plus 4, x plus 6, and so on. So in this picture, because the repeating number of minus 1 to the power of, we get two sets of numbers, and the signs are the opposites of each other, and these two sets. So we, instead of implementing the filter in one set, we have two sets for the odd and the even inside this filter, and the odd and even in that filter. So that's why the code looks like this. But once you figure out how you do it, that's it. And of course, you verify in MATLAB that this is exactly what they wanted. In the bottom, we have a decimation again. Looks much simpler, but here instead of explicitly writing down, spreading out, spelling out all the parts of the filter, here we do it in the loop. So there is a for t, and then we go in the loop and so on. By the way, as we compute the outputs, we take into account the fact that after the filter, the number will be decimated. Only every fourth number will be given, or will be output. So we don't really compute the numbers that will be thrown away later on. Remember, if we look at this, there is this decimation factor here. I think n is a factor of 4 or 5. So every fourth element will be sent out, and 3 out of 4 will be thrown away. So if they are thrown away, we don't compute them. Not very smart, it's a standard methodology. And then we write it into the output. And the question is, kind of self-study. If anybody wants to do it, you can do benchmark, the S-Tech benchmark right away on the modulator with this code. You just take and modify it. By the way, I showed here D mode I, but D mode Q is the same, very similar. And I showed decimation I, but decimation Q again is very similar. So not much, you don't have to do a lot of theory here, just duplicate the code. And the question is what kind of performance, and performance is measured in input range, in megasamples per second. What kind of performance can be achieved on 64 cores operating at 300 megahertz? And we don't take advantage of any special tricks in the core. We only do x86 simple cores in this example. Later on, we will probably need to replace this with a full simulator that simulates the CIMA processor, and then we can answer how much is it improved if you don't take x86 simplified cores, but take the other cores. And here, as you know, what we add to this code is we add a manual count of cycles. We figure out how many cycles each one will take. And we can do it on a simple architecture like x86. In this case, it's really used as a RISC architecture. Or on a SIVA architecture if we understood everything that Hagai told us this morning, how you put 7 of those in parallel and so on. It's not very clear, but what we usually do is, okay, we say, let's say we are excellent and we can do 4 multiplier accumulator per cycles and that's it, and let's not try to beat it beyond that. That's one thing. The other thing that Hagai didn't say in the morning is that we try to never enter this level of either assembly language or C compiled directly and optimized by their compiler. Instead, we take advantage of their pre-optimized function. So we have a library of function and we make a function call. So if we need to do a dot product, we show us a dot product. We don't do it like this, we cheat. We just take his function, dot product, and assume, we know for sure, that the engineers in SIVA have optimized it already for the size that we want. And so we don't really have to go into too much detail. But in the user manual of the function, it tells us how many cycles I should use. It tells, oh, if you have k elements in a vector, a dot product, so your function takes the number of cycles is k divided by 4 plus 7, or something like this. So they give us on the overhead and a way to compute how long it takes if we follow their functions. So this story of B5 code concludes what we wanted to say, and this is the last slide that I showed earlier about the great prize, and this is related, we talked about it, related to a question we never touched today. And this question has to do with your own ability to program or to think about recursion, and one of the key issues in parallel programming, it's not very easy to do recursion, but if you understand how to do recursive code, you understand that everything that you can do with recursion, you can also do with iterations. So the trick is convert the standard code that appears in these 3 out of 4, well, all 4 web pages, convert the recursive code into iterative code, even if you don't know in advance what the number of elements you need to sort. So that's the challenge. Jamin has created a beautiful reward, essay, MacSpace Summer School Grand Finale Competition winner. And it is a gift voucher by Amazon.co.uk, still in the European Union. But 80 pounds.
For the next 2 years.
80, that's what they said yesterday. What Theresa May said, they won't start it until next year. Yeah. And it'll take a long time. Anyway, they have their own currency, so it's 80 pounds. Yeah. You buy from Amazon anything, right? There's no limitation.
So we said that.
Any more questions?
Any chance to get our hands dirty with the real hardware?
With the real hardware?
With the real hardware.
Oh, very good question. So the timetable is this. Well, there are 3 levels of getting your hands dirty. One is this, but your hands keep pretty clean.
Yes.
Hopefully. The next one is a full simulator that includes the actual simulator of the SIVA code 64 times, running for real, and executing everything cycle by cycle, all 64 cores and all other things. And as Jamin or other people will tell you, or you probably may have seen, it will take forever. Not exactly forever, but much longer than here.
Well, with a single core, I mean, on our computers, we were able on our laptops we were able to simulate 5,000 cycles per second.
5,000?
5,000.
It's running in a,
That's what we measure.
a effective clock rate of 5 kilohertz. Fine, you know. For this kind of problems, you finish them within minutes. It's not like here, you know, some of the computation took 2 seconds, 3 seconds, but with a simulator it will take you 2 minutes to 2 hours. But then we look for simulating very large FFT, and we say, anywhere between 1 and 2 days. You gotta have a machine that doesn't crash within 1 or 2 days, but that's easy.
Get in there. This machine is running for 1 or 2 months now. I just closed the lid.
This machine is.
At any rate,
How much are you? 80.
the next thing is the third layer is the hub. Ole is presented here yesterday an FPGA which can fit maybe 1 or 2 or 3 cores. That's not what we mean. We mean the real chip. So our plans right now, we are just now finishing the chip design, and we plan to send it out to TSMC for final tape-out, actually fabrication, during the month of October. That's 3 months from now. They take about 3 months to fabricate and then package, so we will have the chips ready by the end of the year. I've shown yesterday some nice slides with a layout of the PCB. And Ole, well, he didn't show but a layout, but he's doing a second PCB. So there will be 2 PCBs around. One is in evaluation, probably useful only for us internally and DSI and Johnny maybe, to tune and to find out many gory details. But for users to try get their hands dirty, we'd like the second board, the board I showed yesterday, which has place for 1 processor, and that will probably, we are manufacturing the boards right now, but we won't be able to assemble it, of course, until about January or February. So I promise we cannot give you a board before April. But we do plan right after April to start giving away these boards. The nice thing about these boards is that with a standard box that's already available, you connect them to the PC. And everything is on the PC. In other words, the same Eclipse type of interface that's common almost everything and used now and used there too. You're from IBM, so you know Eclipse comes from IBM originally. Some people say, no, they need Visual something Studio from Microsoft, but we don't work with Visual Studio. This time we work with Eclipse. So from your laptop, you should be able to cross-compile and everything and download the code and have the code execute there. So that will happen not before April. Incidentally, the simulator that we talked, the large simulator, allows you simulating not just 64 cores, but it also allows you to debug. So if you really need, you can stop the clock to all 64 cores at the same time, and then go and see what's happening in each one of them. Now we know that they are not syncing, they are not really related. So you don't really need to see what happens at the exact same clock here and there, but it's available. If you're really crazy, you can do it. Of course, it simulates other parts of the chip, and there you may have to. For example, if there is a conflict on the memory access that you don't understand, you want to see what's going on exactly simultaneously. But that's the exception. And the same debugger should be able, we should be able to make it work also on the chip itself. So you can run the chip, and if there is a problem in the chip, you may design it so that, it stops everybody, and now you can go single step or dump everything out and see what happens. Remember, we have full access to all the memory and all the registers, everything on the chip through this RMAP link or JTAG. Take everything out and you see what's going on, so you can debug it. It's a little bit of an overkill because in none of these simulations right now we needed that, but